M&MoCS, modélisation et simulation multi-échelle. It's a pleasure to be here because it is in Arpino. It was in Arpino that I gave my first conference talk, so it is always a pleasure to come back. Today I will try to propose a stochastic high-order continuum model for particle-based materials. When I say particle-based materials, I mean materials that we can model as an assembly of points without considering the shape, the size, the interactions between particles. So basically, without all that physical information that are typical of granular mechanics, that is not the framework of this talk. So the talk is organized, as always, I will try to clarify the context, the research goals, and the applicability of the model. I will propose a pairwise high-order deformation tensor and a model based on this high-order deformation tensor, this stochastic extension, and some numerical results. So let's clarify the context. Basically, the model is specifically developed for materials for which the microstructure is unknown and the interaction between points are not characterized. So we don't know anything about the microstructure. And of course, the classical continuum mechanics is not enough because we are at the micro scale, so we have no local effects. Instead, classical elasticity is local. What are the main research goals? The main research goals is to develop a continuum model that can capture long-range interactions behind Heringer's nonlocal model that is based on the attenuation neighborhood hypothesis that can incorporate higher-order effects, so the effects alla Piola, and that relies on point-wise and pairwise kinematic descriptors. So deformations that are local, but also deformations that are not local for capturing long-range interactions. I will propose the stochastic extension in order to account for material uncertainties, so to perform the uncertainty quantification, because at the micro scale materials are inherently random, and we investigate the role of second gradient effects in uncertainty propagation. So basically, if the randomness of the system changes, if we introduce second gradient effects. Where to begin? In finite deformation, we always use the Green-Saint-Véran tensor. The Green-Saint-Véran tensor is based on a first-order approximation of the configuration function, and it allows, within a first-order framework, to define the difference, to take into account the difference between the squared distance of particles after and before the deformation. This tensor appears in many historical works. I decided here to show the one by Cauchy just for Professor Delisle. In this way, after the conference, he would say that Piola was the first to introduce this tensor. And jokes aside, the idea is to consider an n-order Taylor expansion of the configuration function L and to introduce this pairwise high-order deformation tensor that behaves in a nonlocal framework exactly as the Green-Saint-Véran tensor, defining the difference between the squared distance of particles after and before the deformation. So basically, we can consider an n-order expansion of L. Of course, we need some hypothesis. L must be smooth, must be injective, except possibly on the boundary. And with this Taylor expansion, we have the necessity to introduce this tensor F, that is a pairwise tensor, including all the n-order derivatives. And in the specific case in which the two particles are the same, so x bar is equal to x, this tensor is equal to the uppercase F that is used in mechanics, so it's equal to the Jacobian of the configuration function, or of the placement function, it's the same. I want to discuss the algebraic properties. So, since L is injective, and R is also smooth, the determinant of fx bar x must be non-zero, because otherwise, because we don't want that particles overlap. And for orientation preserving deformation, the Jacobian of R, so the determinant of fxx, must be strictly positive, because otherwise the deformation is not, because otherwise we don't have an orientation preserving deformation. With these two assumptions, we need to assume that the determinant of fx bar x must be strictly positive. So this condition is true for every type of higher order continuum. It's not just true for within the framework of this presentation. For physically consistence, the determinant of fx bar x must be strictly positive. Otherwise, the deformation is not consistent. And the proof is based on the intermediate value theorem. At this point, the introduction of E is straightforward. And in this slide, the approximation symbol is related to the fact that the symbol approximation reflects that the truncation of the Taylor expansion is out of the random. So basically, the equality is not exact. The idea is to use this tensor in order to develop an higher order continuum model. Why? Because it is a pairwise kinematic descriptor. So we have short and long range interactions. I will propose a second gradient continuum model. So we are within the framework of second gradient models, so second order Taylor expansion. And within this framework, we can decompose the non-local tensor in three terms. The first one is local, so there are just first order derivatives. The second one depends on first and second order derivatives. The third depends only on second order derivatives. E1 is pointwise, so it's local. The other two are non-local, so we can use them for modeling long-range interactions. At this point, it seems reasonable, since we don't know anything about the microstructure, that the interaction energy between the two particles is a function of these three tensors, E1, E2, and E1, 2, and E2, but also of the same tensors obtained by switching XX back. Why? Because we need to preserve the reciprocity of the deformation energy, and the symmetry under the change of the two particles ensures the consistency with the interaction, so with the microstructural interactions. We consider the simplest hypothesis. Why? Because the idea is to develop the simplest possible model that is able to describe the greatest number of effects. We do the hypothesis of small deformations. So we assume that the energy is quadratic with respect to the tensor that I just introduced, but under the hypothesis of small deformation. That's the reason for which I use here epsilon and not small case e. We assume that the second order derivatives are negligible with respect to the first one under the hypothesis of small displacements, are negligible if multiplied for constituted parameters of the same order. And we introduce some geometric functions. This is just a definition. Let's say the zeroth moment of the attenuation function alpha. This is an attenuation function on a Reinhard for modeling non-local effects. And the second order moments of this attenuation function. If alpha, so the attenuation function, tends to the Dirac delta in the sense of distribution, N2 is equal to 0. So we have a local model. After a lot of suffering, it is possible to show that this type of interaction energy, so is a pairwise interaction energy, can be represented in a local framework with a deformation energy, here denoted as W, and that is the sum of two contributions. The second one, so the mu EJQ multiplied by kappa, is related to the second gradient of the displacement, and if alpha tends to the Dirac delta, the second term is equal to 0, so basically the model gives back the classical elasticity. But in this way, we have at the same time the higher order effects alla Piola, so the possibility to describe interactions based on double forces, edge contact forces, but also all that kind of features that are typical of Erringen model, so the non-local interactions. So we are trying to mix in the two aspects. The main problem in generalized continua is that we have too many parameters that are difficult to, we can, but it is difficult to identify. And that's the reason for which I decided to introduce the hypothesis 3, that we like to call green type materials. And this hypothesis implies that the constitutive tensors are symmetric in the sense that they satisfy the minor and the major symmetry. Since M is positive definite because of the definition of the attenuation function, and since W is positive definite because it's a deformation energy, then so are the constitutive tensors A11 and A122. So basically we have a second gradient model with features typical of high order continua, Erringen model, and classical models, because we have constitutive tensors that are of the order 4, so fourth order tensors, and that implies some interesting features. Which one? It is possible, under the hypothesis of homogeneity, so the constitutive tensors are spatially constant, and under the hypothesis that alpha is an attenuation function that we choose Gaussian, to introduce an acoustic tensor. Here kappa is the wave number and xi is the interaction length, so the width of the attenuation function, that is symmetric and positive definite. So this acoustic tensor is symmetric and positive definite. That's the reason, and that's good. Why? Because in this way we can apply all the identification techniques based on wave propagation, and that had been developed, they are well known, have been developed in the 90s and have been published in JASAM, Journal of the Acoustical Society of America. So actually they are very standard technique for identification, because we have symmetric and positive definite acoustic tensor, and that allows us to identify the parameters, because if we cannot identify the parameters, the model is not useful. Concerning wave propagation, okay, let's say that if we consider a perturbation, the phase velocity and the group velocity are always different. We can find the analytical expression, and that's the reason for which book wave propagation within this framework are always dispersive. So this model is very rich, but is also very stable, let's say in this way. And
sorry, what is epsilon?
We use the perturbation approach. Okay.
So this small parameter.
Yes. So once developed the deterministic model, we decided to define this stochastic extension that is straightforward. Why? Because the tensors are of order 4, so they are very regular. We define we model the local deformation energy as a net plus value of the random field, uppercase W. In the probability theory, the uppercase lectures are random quantities, instead the small one are deterministic quantities. And just for this presentation, I decided to show some results in a simple case. So in the case in which the fourth order tensors are isotropic, but we can extend all this approach for the anisotropic case, and that's the reason for which we introduced the model, because we can identify the parameters within an anisotropic framework. The first two lambda 11 and lambda 12, are the stochastic representation of the Lermé parameters. And the lambda 12 and lambda 22 are related to second order effects. I will call them Lamé parameters for second gradient effects. We can group them in a matrix, in a random matrix, and we can define a prior probabilistic model. In order to introduce a prior probabilistic model, we need to use the max entropy principle. So we need to maximize what we call the Shannon entropy. And we need also to fix some information, some weak information. Why? Because when we are within the framework of the prior probabilistic model, we need to maximize uncertainties because we don't know the model, we have to construct the model. And we decide to put the mean value of the random matrix that must be finite. We introduce the algebraic representation of this random matrix, and all information are on the matrix-valued random variables uppercase G, and the mean value of this G is implied by the hypothesis on the mean values of the random matrix lambda, but we need also to introduce a second assumption, that is that the mean value of the logarithm of the determinant of these matrix-valued random variables must be finite. Why? Let's say in this way, because this is a very weak assumption that ensures that the standard deviation is finite. So we have very weak constraints that ensures that the mean value is finite and the standard deviation is finite. We know how to generate samples from this model. Why? Because it is inspired by a model that had been developed at the laboratory M&MoCS in 2006. So we know how to generate samples from there, and we can perform the stochastic analysis. I will show a simple numerical applications. The deterministic model is based on the mixed finite element method. The deterministic model is built from scratch from the codes that have been published in the literature by Valle in Gustave, and is based on Phoenix. We adapt a Monte Carlo stochastic solver, and we focus the attention on the axial displacement and the transversal displacement. We don't know a priori the second gradient constituted parameters, so we decide to control these parameters by multiplying the classical one for the parameters theta. So if we change theta, we change the second gradient effects. And in order to clarify the notation, the coefficient of variation is denoted by delta, and n is the number of realization obtained by a Monte Carlo stochastic solver, following the approach that, as I said, has been developed at M&MoCS in 2006. So we built a probability density function using a non-parametric model. The kernel density estimation method is a non-parametric statistical approach. And playing with the second gradient effects, the result is that we have a stiffening effect, so less deformation. If we increase the second gradient effects, we increase the randomness of the system. We increase the randomness of the axial displacement. Instead, we decrease the randomness of the transversal displacement. And this is clear if we look at the coefficient of variation of the axial displacement and of the transversal one. So basically, a priori, we cannot say if we introduce a second gradient effect, then we increase or decrease the randomness of the system, but it depends on the observable. We analyze...
It depends on the wave?
On the observable. So, for instance, if we look at the axial displacement or the transversal displacement,
so
the effective change.
In some waves it is more, in
Yes.
some waves it is less.
Yes. We decided to study also the effect of the correlation length, but in this case nothing changed with respect to the classical elasticity. Why? Because the fluctuations increase for both the axial and the transversal displacements. And we studied the effect of the interaction length, because of the width of the attenuation function. Because the objective in this model is to include in the model the Ehringen's nonlocal elasticity properties. So we have an higher ordered model with nonlocal effects. And we have less deformation, so a stiffening effect. And we construct the interval of confidence. As I said before, if we increase a zeta within the framework of this presentation, we increase the interval of confidence instead of the axial displacement. Instead, if you look at the transversal one, we reduce the interval of confidence. So it depends on the observable.
Which is the percentage of this variation?
Do you mean that the interval of confidence have been built at the 95%? Concerning the quantities, it depends on the value of zeta. So it depends on the amount of the second
Depends
gradient.
also on zeta.
It depends only on zeta. Cioè, basically the difference between the classic elasticity and the second gradient elasticity is this zeta, because we use zeta for controlling second gradient effects.
Okay,
if we change zeta...
Stochastic increase and decrease.
Yes?
How much is in percentage?
It depends on zeta. If I change zeta, I change A. And it depends also on the model. So I cannot say the
So
exact...
can you completely kill second gradient
Yes,
effects
yes.
statistically?
Yes.
So
If
with
zeta
a
is equal to-
certain uncertainty, you don't see second gradients anymore.
If zeta is equal to 0, yes.
Okay. We don't manage to communicate. We will explain it later.
Or maybe I didn't understand the question.
Okay. Go ahead.
I have to conclude. So basically, we introduced the novel pairwise high-order deformation tensor that in some way generalize the L-Lagrange or the Green-Sandberg tensor in a nonlocal framework. We introduce a novel mathematical condition that ensures the well-posedness of the high-order continua, because otherwise the high-order continuum is not physically consistent. So we need the condition on the pairwise tensor F and the hypothesis of orientation preserving deformation. We propose a second gradient continuum model that has pointwise and pairwise kinematic descriptors with asymmetric and positive definite acoustic tensors, so we can identify the parameters without any difficulties, because the techniques are well known in the literature. And we propose a max entropy based stochastic modeling, so that is based on the Shannon entropy. We maximize the Shannon entropy under some constraints, and the second gradient effects can amplify or mitigate uncertainty. These are the work that have been published in collaboration with Professor Suarez, and are the basis of this presentation, and I thank you very much for the attention.